So let's get started. We are going to finish the stuff from chapter 8 that I want to talk about, which is the proof that if you have a complete simply connected Riemannian manifold with constant sectional curvature, then it's isometric to one of the model spaces. We stated that theorem last time. I'll state it again. And also, we proved a lemma at the end of the last lecture, which is what we're going to need to do this. And I'll rewrite the lemma. So lemma from last time, if we have two Riemannian manifolds, and for k equals 1, 2, fk is a local isometry, and M is connected, suppose there exists a point P and M with F1 of P equals F2 of P, and the push forward at P agrees for F1 and F2, then F1 equals F2. Okay, so two local isometries between Riemannian manifolds which agree at a point and whose push forwards agree at a point are the same if the domain is connected. We proved that last time. So now this is the main theorem of this section. Let M be complete and simply connected. Simply connected and constant sectional curvature K, which remember by rescaling, we can without loss of generality assume is -1, 0, or 1, then M is isometric to one of the three model spaces. Let me write them down. Hn hyperbolic, Rn Euclidean, and Sn round metric. And of course, this is k equals -1, this is k equals 0, and this is k is +1. And of course, n is at least 2, otherwise we're not doing anything interesting. Okay, so let's prove this. We'll use this lemma, and I think we'll also have to use the Cartan theorem from last week. We can do A and B at the same time. So we can prove A and B simultaneously. You can see why A and B are similar and C is different, because these guys, not only are they both non-compact and that's compact, but these spaces are diffeomorphic as manifolds. Okay, so first of all, let's write NH for HNG hyperbolic if k is -1, and Rn Euclidean metric if k equals 0, and fix a point P in N, and a point Q in M, and a linear isometry I from TPN to TQM. Okay, of course, we can do that because these are two Riemannian manifolds of the same dimension. That means that these tangent spaces are just positive definite inner product spaces of the same dimension, so they're isometric. There exists an isometry between them. Let's let F be XQ compose I composed XP inverse, and this goes from N to M. And why can I do this on all of N? XP, which goes from TPN to Rn to N, is a diffeomorphism by the Cartan-Hadamard theorem. right? Here's where we're using the fact that, I mean, these are both simply connected, but we're using the fact that the sectional curvature is non-positive everywhere. The Cartan-Hadamard theorem said that if you had a complete Riemannian manifold, and these guys are complete, so we already know that this is a diffeomorphism. So this is defined for all of n. And this one is defined on all of TPM because M is complete. Okay, my assumption is that M is complete. So by the Cartan theorem, not the Cartan-Hadamard theorem, but by the Cartan theorem from last week, since the curvature condition is automatic, F is a local isometry. So let me remind you what the Cartan theorem said. It was exactly this setup, right? We looked at the inverse of one exponential map followed by this linear isometry followed by the other exponential map. And there we had a local result, right? Because we didn't know that these things were defined globally. But here, n xp is a global diffeomorphism because n is non-positively curved and complete. And xq is defined on the whole TPM because mg is complete. And these, of course, and the Cartan theorem said that if you had, you had this gamma and you mapped it over by this phi t to this gamma tilde, and if the curvatures agreed along those geodesics, then the map was a local isometry, right? But of course, the curvatures will agree because exactly how we chose it, this guy has constant sectional curvature k, and so does this one, right? Our assumption is that M has constant sectional curvature k, and we choose A or B depending on whether k is 1 or 0. So this is automatic. So we get that this is a local isometry. And F star at P is I. That's a consequence of the Cartan theorem, but I'm not going to really need that. And then by lemmas H1 and H2 from last week, since F is surjective, a local diffeomorphism and a local isometry, and K is less than or equal to 0, this implies that that F is a local diffeomorphism. So local, what am I doing? Sorry, I'm writing things that are not assumptions. Since F is surjective and K is less than or equal to 0, we get that it's a local diffeomorphism. I'm messing up my logic. Right, this already followed from here. No, I know what I want to do. I already know it's a local diffeomorphism from here by the Cartan theorem. But since F is surjective, K less than or equal to 0, and F is a local diffeomorphism, we get that F is a covering map. That's what lemmas H1 and H2 give us. Okay, we needed surjectivity and the non-positive curvature and the local diffeomorphism. We got that from here. So this is a covering map. And then since M is simply connected, this implies that F is a diffeomorphism. Hence, F is an isometry because it's a diffeomorphism and a local isometry, therefore it's an isometry. Okay, so in cases A and B, it was just straightforward application of this Cartan theorem and these lemmas. Case C is a little bit more involved. Let's let N H be the round metric on the sphere. Fix again a point P in N, a point Q in Sn, and a linear isometry, just as before. Linear isometry. You can see the first problem we're going to have. We don't know that this won't be, in fact, a diffeomorphism onto its image. It can't be because the domain is a vector space and the codomain is Sn, which is compact. But that map is not a diffeomorphism now. Paper in my hand. Let's define a map F, this time from Sn minus, let's let minus P be the antipodal point of P. So Sn minus the antipodal point of P to M by F is xq compose I composed xp restricted to Sn minus the antipodal point inverse. Okay, so this is a diffeomorphism. Well, xp restricted to Sn minus the antipodal point goes from Sn minus the antipodal point. Sorry, it goes from T. Sorry, what am I doing? Xp is a diffeomorphism from TPM to Sn minus the antipodal point. And that's because the exponential map is a diffeomorphism until you hit a conjugate point of a geodesic starting from P. I'll get your question in a second, Vincent. So this is P. This is minus P. We can follow one of these geodesics, and the only place where the exponential map fails to be a local diffeomorphism is when we hit the first conjugate point. But the first conjugate point we worked out for the sphere is the antipodal point. This is the first conjugate point.
Comment on the notation. Do you want to take the classroom question first?
Yeah, I'm doing the classroom question first. Sorry, Vincent, go ahead. What was it? Yeah, but M. Oh, sorry. Thank you. Thank you. That's just that should have been an M. Arthur, what was your question?
I was just getting confused about the P's and the Q's. It's like one point is in the tangent space of the the source manifold. Which is which? Is the P in the source manifold and the Q in the target manifold?
You're right. I've messed up the notation. That's exactly what Vincent was asking as well. So P is in the source manifold. Q is in, what have I done here? This is N.
Yeah.
Did I write it wrong again? Sorry. P is, N is the source. This is N,
the source?
which is, no, no, M is M is the target. M is the target.
Oh, okay.
It's just like we did in case A and B. It was going from the model space into the one we are trying to identify. Okay, sorry about that. So in this case, in order to be able to invert this, we needed to. We know that this actually maps. I've done something wrong here. This is not right. It's not a diffeomorphism from there to there, right? It's it goes from a subset here, right? In order to get to the antipodal point, I have to follow a geodesic for time pi. So this is from the ball of radius pi centered at 0, the open ball of radius pi centered at 0 to here. But that's okay. I can invert it in other words, on Sn minus the antipodal point, I can invert it, and this will map me into here. Then I can apply I, and then and I can do this. Okay, and there's no danger for this, for the output to not be in the domain of xq, because this is defined on all of TQM, since M is complete. Okay, so I've got a mistake in my notes, but it doesn't change what I want to do. So we're going to follow exactly the logic we did in parts A and B. So again, by the Cartan theorem, the curvature condition is automatic because both of these have constant sectional curvature 1, automatic. So F is a local isometry. And now we aren't able to apply lemmas H1 and H2 like we did before. So we're not done yet. We're going to have to work a little harder. Choose a point P prime in the sphere, which is not equal to P and not equal to the antipodal point of P. And let's let Q prime be F of P prime. So notice Q is F of P. Right, the way we've defined the map F, it takes P to the origin and then to the origin, because that's linear, and then to Q. So this is F of P, and I'm going to choose some point P prime, which is not equal to P or its antipodal point, and then the antipodal point of P prime is that, and Q prime is going to be F of P prime. So Q prime and then P minus P prime is the antipodal point of P prime. Okay. So let's let I prime be the push forward of the original map F at P prime. This will go from T P prime of Sn to T Q prime of M. And this is an isometry since F is a local isometry. Okay. Now let's define F prime to be exactly the same thing that we did before, but with the primes and iota prime. Okay, this is going from Sn minus the antipodal point of P prime into M. As before, so this time I chose, initially I started with any linear isometry I to construct F, but now my I prime is the one given by the original F, and I'm using this I prime to construct this F prime. So again, by Cartan, exactly the same thing. F prime is a local isometry, and the push forward of F prime at P prime is I prime. That comes from the Cartan theorem, right? And I prime in this case was F star at P prime. That's how we defined I prime. Okay, so this is coming from Cartan, and then the fact that this is equal to this, that was the definition of I prime. We also have so F of P prime is Q prime by the definition of Q prime. It was defined to be F of P prime. but it's also equal to f prime of p prime by the definition of f prime. F prime is exactly a map that takes p prime to q prime. So we have this, and we have that the push forward at p prime is equal to the push forward of f prime at p prime. That's this thing down here. And moreover, since the dimension n is at least 2, if I look at w, which is Sn minus p and, minus the antipodal point of p and the antipodal point of p prime, this is connected. So if I take the n sphere, when n is at least 2 and I remove 2 distinct points, it's connected. This is an obvious fact from topology. This wouldn't be true if n was 1. So what do we have? We have f and f prime are both local isometries from W. So f and f prime are mapping from W into M. These are local isometries. And f of p prime equals f prime at p prime, and f star at p prime equals f prime star at p prime. So by the lemma that we proved last time, which I stated at the beginning of today's lecture, f equals f prime on W. They agree on W. All right, so now we just have to glue them together. So define a map H from the whole sphere into M by H of R is f of R if R is not equal to minus P, and H of R equals f prime of R if R is not equal to minus P prime. And then by construction, or by the previous result, H is well defined. In other words, if I take a point which is in both, which is both not equal to minus P and not equal to minus P prime, that means it's in W. So an f and f prime agree there. And they're both smooth. So H is a smooth local isometry, because in every point in the domain of Sn, it's either going to be not equal to P and minus P or not equal to minus P prime, or usually both. In any case, it lies in some open set on which it equals another function, which is a local isometry. And hence, so in particular, it's a local diffeomorphism. Local diffeomorphism. But Sn is compact. And this implies that H is a covering map. This is a topological fact. So again, I'm not going to go into the topological details of this, but if you have a local diffeomorphism between manifolds and the domain is compact, then it's a covering map. And this implies that H, since Sn is simply connected, this implies that H is a diffeomorphism, and that implies that H is an isometry. Okay. All right. Sorry, I messed up my P's and Q's and things like that. Let me just make a note here. Okay. Any questions about that? Okay, we are completely changing gears now. We're done with chapter 8. The rest of the stuff that's in chapter 8 is dealing with the case when it's not simply connected, right? So when it's not simply connected, you need a little bit more topology and a lot more group theory, and you end up showing that if you have a complete Riemannian manifold with constant sectional curvature K, then it's a quotient of this model space, the associated model space, by a group of isometries of the model space, a discrete group acting what's called properly discontinuously. So that means you can classify all the complete constant sectional curvature Riemannian manifolds by reducing it to a problem in group theory and topology, which is non-trivial, but it's understood. Okay, yes. No, we don't. No, the map, the statement is that if you have a local diffeomorphism from a compact space to another space, then it's a covering map. Oh, no, sorry. No, you're right. Thank you. You're absolutely right. S is compact and M is simply connected. No, I used, sorry. What am I doing? I'm going from, have I messed this up again? M. Thank you. I have a covering map from, I have a local diffeomorphism from Sn to M. And because Sn is compact, this is a covering map. But then I have a covering map from Sn to a simply connected space. That means it's a diffeomorphism. Okay, another mistake. Oh no, I wrote the right thing in my notes. I just didn't say the right thing in class. So now we're moving on to chapter 9 of De Carmo. We're going to do this whole thing in detail. In chapter 9, we introduced the variational point of view to studying geodesics, right? So we're going to talk about the energy functional. I'll say a little bit about the length functional. They're basically, in some sense, equivalent. We're going to show that geodesics are critical points for the energy functional in the sense of calculus variations. And we're going to compute the first and second variation formulas for the energy functional. And we're not going to do all of this today. We're going to start. The second variation formula is going to be a tool that we're going to use for the rest of the course and for the rest of the lectures. And you're going to see basically the Jacobi equation showing up again in the second variation formula. So the Jacobi fields are going to be related to second variation of the energy functional at a geodesic. So this is variations of energy. Okay. A lot of the stuff from earlier in the course will come back here, like the symmetry lemma and the commuting covariant differentiation along curves. All the stuff that we did in chapter 5 is going to come back. Okay, so the punchline, so we'll show geodesics are critical points of the energy functional. We'll compute the second variation formula. Second variation of energy, I'll tell you what energy is, at a critical point. And this will be related to Jacobi fields. Although the full relation you're not going to see in chapter 9, we'll see it a little bit later. And then we'll use this in this chapter, we'll use this to prove two big global results. The Bonnet-Myers theorem says that if it's complete and Ricci bounded strictly above 0, then it's compact. I'm going to give a precise statement on Wednesday, right, or probably Monday of next week. And the Sinji-Weinstein theorem says if it's compact, orientable, even dimensional, and positive curvature, positive sectional curvature, this implies it's simply connected. And we'll see that all of these hypotheses are needed. You can't remove any of them. They're examples, counterexamples to any of them. So in both of these theorems, you make some assumption, some mild global assumptions. Well, completeness is not, if you don't have completeness, at least you really can't hope to say anything. So and we have a local assumption, which is about the Ricci curvature, and we conclude a global topological consequence. So here, compact is a stronger form of completeness. These are all topological assumptions, and then we have a curvature assumption, and we get another powerful global topological consequence.
Question?
Yep.
So when I've seen this done variationally, it's the distance, not energy. What's the
Yeah, that's what I'll start out with now. There are reasons. So the question is why are we doing energy and not length functional? I'll show you why the energy functional is easier to work with than the length functional when I define both of them in a minute. Okay, but you can do it with the length as well. Just a little more tedious to do it like that, and I'll tell you why this is preferable. Okay, so let's start. Let alpha be a piecewise smooth curve. Defined on some closed bounded interval starting at 0. We can just shift the parameter to make sure this happens. A variation of alpha is a continuous map sigma from minus epsilon epsilon times 0a into m, such that sigma of 0t is alpha of t for all t in 0a, and such that there exists a subdivision, finite subdivision T naught, which is 0, and then strictly less than T1, T2, Tn minus 1 less than Tn, which is A, when such that sigma restricted to minus epsilon epsilon times Tk minus 1 Tk is smooth for K equals 1 up to n. Okay, so in other words, if I, well, let me say, okay, that's the definition. I'm going to draw a picture and I'm going to say more about how you should think about this definition in a second. So let me just add one more definition. The variation is called proper if sigma of s comma 0 is alpha of 0 and sigma of s comma a is alpha of a for all s in minus epsilon epsilon. Okay, so and finally, well, if sigma is smooth on the whole domain, then the variation is called smooth, and it's called a smooth variation of alpha. So let me draw a picture. It's probably easier to draw the proper variation first. So here's a curve alpha. This is alpha of 0, alpha of 1. So for every, the way you should think about a variation is for every s in minus epsilon epsilon, if I look at sigma s, which is sigma of s dot, then this is a map from 0a to m is a piecewise smooth curve. Okay, so I think of sigma of s, sigma sub s, where you fix s as being a curve with the same domain and the same places where it could potentially have a jump in the velocity vector, and so it's a one parameter family of curves that are deforming, that are varying the curve alpha, because when sigma equals 0, when s equals 0, I get alpha. Right? That's what part of the definition is. So here, if the variation is proper, let's say it's also smooth. Right? So this could be sigma s for some time s, for some parameter s, right? And as s goes to 0, you get the curve alpha, and maybe this is s from 0 to epsilon, and maybe this is s from 0 to minus epsilon. So this is a picture of a smooth proper variation.
Question.
Yep.
So if the variation is smooth, does that imply alpha is smooth?
No. Yeah. Here. So my definition of what it means to have a smooth variation, that's right. It means that sigma is smooth on here. So if I restrict it to s equals 0, then alpha is also smooth. So you can't have a smooth variation of a curve if the curve is not already smooth, right? But if the curve is smooth, you can have variations which break the smoothness. I'll try to draw some more pictures now. So here's a picture where we have a proper variation, and let's take n to be 3. Okay, so alpha this is alpha. There's 3 places where its velocity can jump, and then this one is still proper, so it'll be something like there'll still be 3 jumps. Oops, it has to go back to there. So sigma s, right? And I can have a whole bunch of these. So I mean, I do have one of these for every s from maybe this is sigma of s prime. For every s in minus epsilon. Okay. So you want to think of it as a continuously varying, well, it's continuous. In S, it varies smoothly, right? But in T, you can have a finite number of jump discontinuities in the derivative, in T derivative. And then to draw a non-proper, let's try a non-proper smooth. It's harder to draw these because they don't have to have fixed endpoints, but maybe this is alpha. And there's no reason why they don't cross, right? You have even there, they could still cross. I have a smoothly varying family of curves passing through the curve alpha at s equals 0. So a variation sigma of alpha is a smoothly varying in S family of piecewise smooth curves sigma s with sigma 0 is alpha, and a proper variation means that the endpoints are held fixed.
So in your definition, you just said sigma had to be continuous.
No, in the definition, I said it has to be continuous, and that when you restrict it to each of these pieces, it's smooth, right? So that just means that the same subdivision breaks up this piecewise smooth curve into a bunch of smooth curves that glue together continuously for all s, right? So there's no reason why, all of these sigma sub s's have to have a jump in their velocity at each of these TKs. They could have a C1, they could be C1, so their velocity could be continuous even at those points. In this picture here, if we go back to this picture, I drew alpha here with 2 jumps, but it could be that some of these sigmas have less jumps. Maybe this one only jumps at T2 and this one only jumps at T1. That could happen. But the point is, there's only going to be a finite number of jumps for any of these sigma s's, And we can choose them. This is part of the definition of a variation. We can choose a single subdivision of 0 to A into n pieces so that all the jumps for any of the sigma s's can only occur at those TKs. Does that make sense?
So it's continuous on the interval, well, the kind of the square interval minus
continuous.
epsilon to epsilon cross A to 0. So it's a continuous function on
Yes, that's
that.
right. It's continuous
But
on this.
for each value of the first parameter, the result is piecewise smooth. Piecewise smooth. Yeah.
The piece, yeah. So if you, that's what this is circled in here, right? So in other words, sigma s from 0 to A to M is piecewise smooth.
Okay.
For all s as a function of t, right? And the places where the jumps can occur are all at the same places for any s. That's part of the data. Okay. Of course, you can come up with more general variations that don't have this nice property, but we're not going to need them for what we want to do. Right? This is the most general class that we need. This is what I last wrote, so I can erase this.
So are you doing it that way to
Hang
avoid
on, Arthur, I've got a
introducing?
question here. 1 second. Go ahead.
Oh, sorry.
Mm-hmm. Yeah, so the question is, can you put a smooth structure on the space of maps? And you can. It's more complicated because there's an infinite dimensional smooth manifold. The space of smooth curves, even with fixed endpoints, the space of smooth curves between two or piecewise smooth curves is a smooth manifold, but it's infinite dimensional. And we're trying to avoid having to define what an infinite dimensional smooth manifold is. That's why we're putting in all these assumptions to make something very concrete. But yeah, you could talk about that. It's not what's usually done in any first time you see this kind of stuff, because it's going to make it unnecessarily complicated. Arthur, you had another question?
That's exactly what I was going to ask, because the normal treatment is you introduce some kind of Banach space on the functions.
Yeah, we're not going to do that here. We're going to keep it more down to earth. Okay. Okay, so for a fixed t in 0a, the curve s goes to sigma of s. Let's call it fixed t naught. Right? Or no, I've called t naught something else, t hat. S goes to sigma of s t hat is called a transversal curve to the variation. So let's see if I can draw some pictures of that. Go back to our pictures here. So maybe something like this, right? These are sigma of s, sigma dot of some fixed value of t. And these are transversal curves. And you can see that for a proper variation, the transversal curves at t equals 0 and t equals a are just constant curves. Okay. Now, that's the definition of a variation. Given a variation, we're going to get a vector field along alpha. So given a variation sigma of alpha, define v at t to be d by ds at s equals 0 of sigma of st for t between 0 and a. And where does this thing live, v of t? If I'm fixing t, and I'm thinking of this as a curve in S, this is one of these transversal curves, these yellow curves I just drew. So I'm looking at the velocity of one of these transversal curves at S equals 0. So that's going to be a tangent vector to sigma of 0t of m, but sigma of 0t is alpha t m. Okay, so hence V is a vector field piecewise smooth vector field along alpha.
So is it
Um,
obvious that the transversal curve is actually differentiable?
That was part of the assumption. The question is it obvious that the transversal curve is differentiable? The assumption was that sigma is smooth on each, when you restrict sigma to minus epsilon epsilon times t k minus 1 tk, it's smooth. Okay, so then if I fix a value of t, I'm going to get so this is why I say piecewise smooth, right? So at these points, the TKs, there could be a jump because I'll have a left-hand limit and a right-hand limit. Let me put that. It's worth saying it because it's going to come up several times today and Wednesday. So notice if t is not tk for k from 0 to n, then v of t is well defined. But if t equals tk, then we get v at tk plus is the limit as t goes to tk from above of v of t, and v of tk minus is the limit as t goes to tk from below of v of t. These can be different. So that's why I say v is piecewise smooth, right? It's a vector field along gamma, but it can have jump discontinuities in v. Sorry, so I see what you're saying. It's not piecewise.
Like you're
smooth.
not saying it's differentiable in the two variables.
Yeah.
You're only saying it's kind of
No.
continuous in the first
That's right.
variable.
It's not even continuous in T, right? So is a vector field along gamma, let's say a rough vector field along gamma, and for and it's smooth on tk minus 1 tk on the open intervals, right? In between these points where the velocity of alpha can jump, v is perfectly well-defined smooth vector field. At the points is not even continuous, it can jump. That's what I meant to say. That's better. Okay, so it's not a smooth, it's not even a continuous vector field along alpha. It can have jump discontinuity. Okay. And now let's just say this V is called the variational vector field of the variation sigma. So now I wish I hadn't erased that picture. Let's draw it again. So here's some, this is a proper smooth variation. Here's my transversal curves. So V is the velocities at s equals 0 of these transversal curves, right? So here it's a nice smooth vector field. Here, you can see away from those points where the velocity vector jumps, there's no problem. This is going to be v of t1 minus as we're coming from below, and this one here is going to be v at t1 plus, right? I'm looking at the transversal curves. I'm looking at the velocities of the transversal curves at s equals 0. As t is going to t1 from below, I'll get this blue vector. As t is going to t1 from above, I'll get this blue vector. So it's got two values at these points tk, right? We have a left-hand limit and a right-hand limit.
So I'm not even worried about those those nodes. I'm just worried about going from one curve to the next, because don't you need something like more like uniform continuity in order to get
What do you mean by one curve to the next? Which curve to which?
Like to go from, so the velocity
Mhm.
of the transversal curve is connecting, kind of one kind of candidate geodesic to another. But
These are not
don't
geodesics,
you?
these are just curves, right?
Yeah. I mean, I call them candidate,
Okay.
whatever you want to call them,
Yep.
paths.
Yep.
We'll call them paths.
Yes.
But just going from one path to another, I don't know if continuity is enough to get a
No, we don't.
tangent vector.
We don't have just continuity. These sigma t, which is sigma dot t, is smooth.
Yeah, but it's not smooth in
On-
the first variable.
It is.
And that's
what I'm saying. That's the definition. It's smooth. That was the definition. It was smooth on minus epsilon epsilon times tk minus 1 to tk. So if you fix t, if t is not one of the tks, and you fix t, then sigma, the transversal curve is perfectly smooth. When t is equal to one of the tks, then what does it mean to be smooth? I can take, let's say, I can take sigma restricted to t1, t2, sorry, minus epsilon epsilon times t1, t2 is smooth. And I can take sigma restricted to minus epsilon epsilon t2, t3 is smooth. Okay, so what does it mean to be smooth on a closed interval? It means it's the restriction from a smooth map on an open interval to that closed interval. And that map is not going to be the same in these two cases. In this case, there's some smooth map that's defined on some open set containing this, which restricts to this guy. And in this case, there's a smooth map defined on an open set containing this one, which restricts to this guy. And those two smooth maps are not the same, right?
Yeah.
And therefore, that's why you're going to have a different velocity that's why the V's are going to be different. You're going to have a VTK minus and a VTK plus. But for each of these, there is an open set containing this domain and a smooth map which restricts to this guy. And you fix, let's say you fix T to be T2 and you use that map, it's smooth in S. And here you have some other map which restricts, smooth map which restricts to this. You fix T to be T2, it's smooth in S. You'll get a different V, right? But in both cases, for a fixed T, it's smooth in S.
Okay, yeah, that's fine.
Okay.
I just thought your original definition didn't require it to be smooth in S, only continuous.
No, it did, because I said smooth on minus epsilon epsilon times tk minus 1 to tk for every k. And that means smooth in both variables, right?
Well, I thought the original definition only said it had to be continuous, not smooth.
No, I said it. No. The definition of a variation was that it was continuous on this,
right?
And smooth on minus epsilon epsilon times tk minus 1 to tk for all k.
Okay, that's fine. Sorry, I didn't pick that up.
That's okay. All right. Okay, so now we have, given a variation, we have this vector field V, which really, strictly speaking, can have is not well defined at the TKs, right? There's a left-hand limit and a right-hand limit. Now, what we want to show is that if you have any vector field in this sense on a curve, then it is the variation vector field of some variation. So that's the following proposition. Given a vector field V along a curve, along a piecewise smooth curve alpha, where let me put in quotation marks, vector field V such that, so V at T is in T alpha Tm for all T, V restricted to the open interval Tk minus 1 to Tk is smooth for all K from 1 to N, and V of Tk minus need not equal V of Tk plus, right? So you can have jump discontinuities. But suppose I have, essentially what that means is I have a smooth vector field on each of these closed bounded intervals, but they don't have to patch together to be continuous. Okay. Then let's write the statement of the proposition. Then there exists a variation, sigma, whose variational vector field is V. And moreover, well, let me just write it. Then there exists a variation, sigma, whose variational vector field is V. Certainly not unique. Field is V. And moreover, if V at 0 and V at A are 0, then we can choose sigma to be a proper variation. So the proof, the picture for this proposition, let's put in some corners. Here's let's say this is V. And you see I've given it two values at this branch point here. I don't want to call it a branch point. This point where there's a jump in the velocity of alpha. I'm saying that we can find a variation sigma of alpha, whose variation vector field is V. And moreover, if V vanishes at the two endpoints, we can choose this variation to be proper. Okay, so let's see how that works. Okay, so we know that the image of alpha is compact because it's the continuous image of a closed bounded interval. Let's let T be a time in 0A. There exists a totally normal neighborhood WT delta T of gamma of T, sorry, alpha of T, my curve is alpha. Remember, what does that mean? That means that this is a normal neighborhood, and so WT is a normal neighborhood of alpha of T, and the exponential map WT is contained in the image of XQ of B delta T0 for all Q in WT. It's contained in a normal neighborhood of each of its points, a geodesic ball, normal ball in each of its points of the same radius delta T. We saw earlier in the course that we can do this. So we have the WTs for T in 0A is an open cover of this compact set. So there exists a finite subcover, i.e. there exists these are not the same T's as the ones in the let's call them B1 up to BM in 0 to A, such that alpha of 0, 1 is contained in the union of J equals 1 up to M W Bj. And let's let delta be the minimum be the minimum of delta 1 up to delta m, where delta j means delta of bj. Okay, and this is positive. Okay, so what we've done is call this so by construction, exp alpha t is defined on b delta 0 contained in t alpha tm for all t in 0a. In other words, I find a uniform time of existence for the exponential map everywhere along this curve. Maybe it's worth saying it again, but slightly differently. I.e., for all t in 0a and v in t alpha t of m with norm of v less than delta, exp p of v is defined. Exp alpha t of v is defined. Okay. Now let's let. Yep.
So you've introduced the metric here, but does this only apply to Riemann this proof? Like, is it essentially dependent on the thing being Riemannian, or doesn't this work for an arbitrary manifold? You could just use coordinate.
Well, I can introduce. So the question is, the question is, I've introduced a metric to do this proof, right? I could introduce. I mean, we've had a Riemannian manifold the whole time. The statement of the proposition doesn't involve a metric. I introduced a metric. I'm going to prove it, and then the result is independent of the metric, right? So it doesn't matter which metric you took, but I think you do need you need to choose a metric. Well, there may be a way to prove this proposition without using a metric. This proof, of course, uses a metric, but because the statement of the proposition is independent of any metrics, it doesn't matter which metric I chose. Okay, there's possibly a proof, a metric independent, a proof that doesn't require the use of a metric, but that's not what I'm going to do here. Yes. Oh, no, it's A's. Yeah. Sorry. I'm making a lot of mistakes today. Okay. So let's let K be the max over all T in 0A of capital V of T. Okay, so we have to be a little careful here, right? Because this guy is not continuous, but remember that V restricted to TK minus 1 to TK is smooth, hence continuous. This is a little bit sloppy what I'm writing, right? I'm saying there is some okay. I don't want to introduce too much notation and make it take longer than it needs to. This is well defined. Why? Because there's a limit. There's a limit to V. I guess in the definition, what I should have said is that for each k from 1 to n, there's some smooth vector field on alpha restricted to tk minus 1 to tk. Okay, and then we put them together to get this vector field V. They may not agree at those TKs. They may jump, but that's okay. On each of these closed bounded intervals, we have a continuous function. So it's the norm attains a global max on that interval, and we have finitely many of these partitions, right? So this is well defined. It's well, I can assume that V is not identically 0. The only way this will be 0 is if V was identically 0. But if V was identically 0, I can take sigma of S comma T just to be alpha of T, right? And that works. That's a variation of alpha, and it gives me capital V is 0. So I assume V is non-trivial. Okay, so I have this positive real number k, choose some epsilon with less than delta over k, positive, and define sigma from minus epsilon epsilon times 0a into m by sigma of s and t is I take alpha of t and I apply the exponential map to s v of t. Okay, this is well defined. Because s v of t is equal to s times v of t, which is less than s. Oh, s is less than epsilon. This is less than k, and that's less than delta. So because this vector has norm less than delta, I can apply the exponential map to it. And now I can already anticipate the question, what happens at the places where v has two values? Okay, let me think about this. See, Docarmo doesn't even talk about, he certainly says that V has jump discontinuities at the TKs, but that's going to give me that sigma is going to have jump discontinuities. Why is sigma, this is not right. Okay, I'm not seeing it right now. I have to think about it carefully. Let's ignore for the moment what's happening at the TKs, because I have a feeling he's got a gap in his argument that I didn't notice when I was writing this lecture. So I'm probably going to have to modify it and let you know. So let's ignore the TKs for the moment until it hits me what's going on. What is sigma of s and t? Alpha t of s v of t. This is equal to gamma of time 1, where gamma is a geodesic with gamma of 0 is alpha of t. And so let's say this is a function of s, and gamma prime at 0 is v of t. So gamma is a s goes to gamma of s for s in minus epsilon epsilon. That's just because of the definition here. And recall from the ODE theorem, gamma depends smoothly on the initial data, which is the initial point and the initial velocity. Hence, the map sigma is piecewise smooth. And I know there's a problem here because this map is not well defined as the TKs. So I have to think about what's going on here, and it's not immediately obvious to me. Maybe my variations also jump at the TKs. So there's a gap here. There's a problem here because sigma s tk is not well defined, right? Because v of tk plus need not equal v of tk minus. So maybe the issue is that the definition, he was probably sloppy in his definition of a variation, and he probably probably does not. Sigma itself probably jumps at the TKs. So I'll fix this and I'll get back to you. Yeah.
You probably don't care, right? Because the
No, I
functionals
don't care.
are only going to define, they're not going to,
Yeah.
they're only going to depend on, it can be discontinuous on a set of measure zero, basically, for the
That's right.
functionals you're defining. So who cares? Like,
Exactly.
you do it for the
Yeah,
smooth
no,
case, it's probably
right.
enough.
Yeah, exactly. So what Arthur says is right. It's not going to matter, right? What I should have said is that the sigma itself could have jumped discontinuities of the TKs, right? Because that's what we're getting here. We're getting a sigma that has jumped discontinuities at the TKs. It's not well defined there, right? And it doesn't matter because what I'm going to do with all these things is integrate. And there's a finite number of points where bad things happen, and that doesn't affect the integral at all. Right? So probably the original definition, and this is almost certainly what it is, the original definition of variation should have allowed for jump discontinuities of sigma at the TKs. Because this is what's happening with the sigma that we're getting here. Okay. Now, all that's left to check here is that the variation vector field of this sigma is V, and that if V vanished at the two endpoints, this would be a proper variation. So remains to show that V is the variational vector field of sigma. And if V of 0 equals V of A equals 0, then this is a proper variation. Oh, by the way, why is it a variation? It's a variation, I should have said that, because what happens when we plug in S equals 0, so it's a variation because sigma at 0 t is exp alpha t of 0 times V of t, and that's just alpha of t. Okay. Now let's compute what is the variation vector field of this variation. That's d by ds. We've done this kind of thing before. At s equals 0 of x alpha t s v of t. But that's exactly, if we think of t as fixed and think of s as the parameter, this is the geodesic with initial point alpha t, initial velocity v of t, and we're taking its initial velocity. This is v of t. Okay, so v is the variation vector field of sigma. And if v of 0 equals v of a equals 0, then what do we get? Sigma of S0 is x alpha 0 of S times V of 0, but that's 0. And then that's just alpha of 0 for all S. And similarly, sigma of SA is alpha of A for all S. So if the vector field vanishes at the two endpoints, this variation is proper. Okay. All right, I will confirm at some point today when I have time that what I said there is correct, that all we have to do is just remove the assumption that sigma is continuous at the TKs, which is almost certainly the case. All right. We have 4 minutes. Let me define two functionals. Right? So let's let alpha be piecewise smooth, and let sigma be a variation of alpha. We don't assume that it's proper. Okay, so sigma is defined on some minus epsilon to m. Define the length function L, which is from minus epsilon epsilon to the non-negative reals associated to this variation, to be, well, the length of at time s, at parameter s, is the length of sigma s. So that's the integral from 0 to a of the sigma dt, right? I take the, remember for fixed s, as a function of t, sigma s is a curve from 0, comma a to m. So this is just the velocity of that curve, and I just take the length. Define the energy function E from minus epsilon epsilon to the non-negative reals associated to sigma to be. So instead of integrating the length of the curve, the length of the velocity vector, there's a 1/2, and we integrate the length squared of the velocity vector. So let me just make a remark. Though Carmo doesn't have the 1/2. So Carmo doesn't have the 1/2, but everyone else does. Okay, so his energy is twice the usual energy. Why is this the standard thing to do? Obviously, if you know some physics, this is a velocity squared, 1/2 times the velocity squared. Let's say the mass density is constant. This is like a kinetic energy, right? You're adding up a bunch of 1/2 velocity squared, speed squared, kinetic energy. But there's other reasons to put the 1/2 there, because we're going to differentiate this guy, and the 2 is going to come down and get rid of the 1/2. So we're going to lose these factors of a 1/2 once we differentiate. That's why we want to put them in there, so we don't have unnecessary factors of 2. One reason why the energy is better, E is better than L, is because the function norm squared is better than the norm, right? Because the norm squared is always smooth everywhere. The norm is continuous everywhere, but it fails to be smooth at the points where the norm vanishes, right? Where at 0. So that's one issue, but also well, I don't have time now. I'm out of time. So next time we'll see how E and L are related. They have essentially the same critical points. And maybe I'll say it in words, but I won't write it down because I'm out of time, but I will write it on Wednesday. Critical point for the length functional, you know that the length is independent of parameterization. If you reparameterize your curve, the length stays the same. That's not true of the energy. And the energy is not independent of reparameterization. So if you find a critical point for the length functional, any reparameterization has the same length. It's going to still be a critical point. So what turns out to be the case is that the critical points of the length functional, if they're constant speed, are the geodesics. Okay, so if you have a critical point for the length functional, then you can reparameterize it by arc length, and you're going to get a geodesic. But if you have a critical point of the energy functional, it already has to be constant speed parameterization, and it has to be a geodesic. Okay, so you sort of don't have to worry about this ambiguity of reparameterization by using the energy. Okay, so we're out of time. I will explicitly show the relationship here between the critical points next time, and or maybe not the whole thing, but I'll do a little bit. Then we're going to compute the first and second variation formulas. That's probably going to take the whole lecture, and then next Monday we'll do the applications of this, which is the Bonnet-Myers and the Sinji-Weinstein theorems. Okay.